Oh, great. So my name is Noam Soker. I'm from the Technion in Israel, and I will be, my translation name is Pleasantness Review, and I will give you a short review on what I've been doing in the last 8 months. And this is comparing evolution of AGB star mainly, also RGB, to progenitor of supernovae. So not all of you are familiar with supernovae, but this is a short review. So let us start. Okay, what is my goal? My goal is to learn about core collapse supernovae and their progenitor from AGB stars and planetary nebulae. What is the main motivation? Not only, but main. There is a debate on what is the explosion mechanism of core collapse supernovae. There are those who believe in delayed neutrinos, like a group in Monash University, Bernard Miller, but I think that jets explode all massive stars, and I will try to convince you, because you are familiar with jets in our systems, that this is the case. So I will touch upon 2 subjects. One is concerning the evolution before the explosion, and I compare what I call the effervescent zone model, which is the extended zone above the photosphere of rising and falling clumps alongside the regular wind. And I will touch upon it first. Then I will talk about jets. Let us start with the effervescent zone model, which I built it a long time ago in 2008. In a paper. It's a phenomenological model for the extended zone above asymptotic giant branch star. And I will show you later when I expect it to exist. And effervescent, those who don't know, is the bubbling of, like here you see in a drink. So what I had in the old paper on AGB star, the wind and bound gas exist simultaneously to distance of about 100 AU. And this is the effervescent model. And why did they build it for AGB star? This is to allow wide binary companions to influence the morphology of the descendant planetary nebulae by accreting mass from the effervescent zone. This is in addition to what Shazrin Muhammad talked about earlier this day, about accretion from the wind, Roche lobe overflow from the wind. I think the effervescent model is more efficient even. And I think the difference between the effervescent model and the wind is that wind, all material escaping. In the effervescent, not. Some parcels rise and fall back. So accretion from the effervescent zone is more efficient than accretion from the wind in forming accretion disk around the companion. The companion might then blow 2 jets that will shape the descendant planetary nebula. This is an old paper on AGB star. Okay, so then in 2021, just 2 years ago, I build the same model, but for progenitor of core collapse supernovae, meaning stars of 8 solar masses and more. And the main difference between the wind is that here pulsation and convection in the star play crucial role in uplifting parcels of gas that do not reach the escape velocity. They rise to a distance of several times the solar radius, to tens of times the stellar radius. So it's about 30 to 100 astronomical units. The density of the bound mass can be tens of times that of the regular wind. The dense effervescent compact circumstellar zone can explain several things in a core collapse supernova explosion. They can explain the collision of the ejector of the supernova with a circumstellar material, CSM circumstellar material. It can facilitate a very high mass loss rate if the star experiments powerful pre-explosion activity. It can form dust to obscure the star. It can lead to efficient mass transfer to a companion. Okay, the effervescent zone might exist for thousands of years and more, removing the requirement for many type 2 core collapse supernovae progenitors to experience a very strong outburst just prior to explosion. So people observe that the ejector of core collapse supernova, these are supernova of massive stars, collide with circumstellar material, and they explain it by some activity few years to just few weeks before the explosion. So there's an outburst, and we do observe it in some cases. However, I will present you very, very recent observation where the core collapse supernova did not have a pre-explosion outburst. The first one is this supernova from 2023, about a year ago. The light curve indicates interaction of the supernova ejector with a dense, compact circumstellar material, and this is a supernova in the galaxy. Okay, and the conclusion from the fitting of the light curve and spectra is that the circumstellar medium extended to about 30 astronomical units, and the mass was about 0.01 solar mass. The puzzle is that this supernova did not suffer any outbursts for tens of years before the explosion. It cannot be that this circumstellar medium came from an outburst or something. So the recent observation of another supernova points to the same. This is a supernova from last April, just a few months ago, and indicates interaction with an extended circumstellar medium just for 40 astronomical units. This is not large. It's a star itself was probably 2 astronomical units, so it's only 10, 20 times the stellar radius. The mass was a little bit more, maybe 0.1, 0.4 solar mass. The puzzle is again that this supernova did not experience any outburst. There is a model with an extended wind acceleration zone, but in a recent paper that was accepted by AstroPH, I showed that this is problematic. Okay, so what is the effervescent model that I talk? We have clamps that are ejected by strong pulsation and strong convection. They eject the clamp and the clamp falls back, and I claim in some cases it exists in AGB star and also in progenitors of core collapse supernovae. And this is the effervescent zone, clamps going up and down, and the distance between 10 and several tens the stellar radius. Okay, when do we expect the effervescent zone? This is expected only when the radiation cannot accelerate anymore, namely when the mass loss rate is the maximum that the luminosity can supply. And here a scaled quantity, not to AGB star, but red supergiant progenitor of core collapse supernovae, and you see the luminosity is 10 times 10 to the 5, and the velocity, escape velocity is 100, not 10. But the mass loss rate is quite high. It's several times 10 to the -5, and eta wind is the number of times the photon is scattered, around 1, okay? But the key that to uplift this material needs strong pulsation and convection, and indeed in the progenitor of the supernova from 2023, there were observation before the explosion of very strong pulsation. So here is some property of the effervescent zone. The density KB on the lower equation is the density of the clamp relative to the wind. It's hundreds of times denser. It's just photospheric material that pulsation and convection just eject out, and they are falling back. And this is a model. The filling factor is low. The clamp's filling factor is 10%, a little bit more, maybe a little bit less. And there are parameters here again for supernova progenitor, which is the effervescent zone radius here is 30 AU, like the progenitor of the supernova. The mass is 0.01 solar mass. The velocity is 100 kilometers per second because it's progenitor of core collapse supernova, and the mass loss rate is very high. And this is the effervescent model. A new model from last May came with another scenario, which we call boiling model, but it's the same, probably the same mechanism, but they did much better job in doing it quantitatively, and they also came to the conclusion that we have parcel of gas going up and down. Let's go to the second topic where I think we can study from AGB about progenitor of core collapse supernovae. So the previous one was spherical or non-spherical. If there is rotation, parcel of gas that going up and down, no companion needed, no jets are needed. But now I'm going to a great debate over the explosion mechanism of core collapse supernova, between the neutrino that probably you study in school, the young people, and the jittering jet explosion mechanism, okay? So in a series of papers in the last year, actually it's less than a year, I demonstrated the similarities of core collapse supernovae with point symmetry to other jet-shaped astrophysical objects. Okay, so let me go to comparison. Let me start with planetary nebulae that many of you are familiar with. There are different planetary nebulae here in the picture, and I define what is called a rim nozzle asymmetry. Namely, you have two lobes inflated by two opposite jets, but they are not symmetric. In one, you see a rim closing the bubble. In the other, you have opening, kind of a nozzle, like the jet escape outward. And with the blue dashed line, I show the nozzle and rim. And there are many cases. Let us take one of them. But before I take one of them, here is a cluster of galaxy. Here we see the jet in radio, which I will not show you here. But this is an X-ray image of a cluster of galaxy. You have the name here. And you see bubble. Again, you see bubble inflated by jet. We know that our jet we see in radio. We see a rim and a nozzle. And here is a supernova 87A. When it exploded, I was a young postdoc. Some of you were not born yet. We also see the center, and we see here two bubbles, one with a rim, one with a nozzle. And this is not the influence of the circumstellar medium, which is a ring that you see here. The ring you see here was ejected 20,000 years before the explosion. It did not influence yet the ejector, and we see in the ejector clear structure of rim nozzle asymmetry. And this is my comparison, my first comparison. You clearly see rim nozzle asymmetry in supernova 87A, and you see here the rim nozzle asymmetry in two planetary nebulae on the right and in the cluster of galaxy on the bottom. This comparison tells me that, well, supernova 87 was exploded by jets. There is more to supernova 87A. I identified in a separate paper, identified 3 clumps on each side, where when I draw lines between these clumps, I reach the center. The lines go through the center. This is point symmetry. The point symmetry is common in objects shaped by jets. More than that, supernova 87A have 2 arcs. These arcs are the structure around a barrel shape. It's going around axis symmetry, but the projection, a limb brightening give you 2 crescents or 2 arcs. And there is another supernova with this supernova remnant with this structure. So there are 2 supernovae here. On the upper, you see 87A, and the bottom 2 images of the same one, where you see 2 pairs of arcs. And here are 2 planetary nebulae on the right with 2 pairs of arcs. So clearly, for me, clearly these supernovae were exploded by jets. And actually, you see the jets going out. On the lower left, you see a core collapse supernova with the jets going on. We have another supernova, as another planetary nebula, NGC40, with such a jets going out like a chimney. And the double arc structure is common in planetary nebulae. And from this, I use planetary nebulae, which are descendant of AGB star, to study about core collapse supernova. Here you see the pairs of arcs in the planetary nebula. Let us look at this very new core collapse supernova. So 3 images here. Look on the upper left, you see 3 rims on the lower right, and you see a nozzle in the upper left structure of a newly identified core collapse supernova remnant. This year by FESED, it was announced this year. On the upper right, you see planetary nebula. Again, you see nozzle in one pipe here on the lower right, and in one lobe, and you see 3 rims, which are activity of jet on the other lobe. Look at the lower right. You see cooling flow galaxy cluster, cooling flow galaxy. This is a cluster of galaxy, and you see 3 rims by the jet. The blue colors are jet. We see the jet giving 3 rims. On the other side, you don't see. So these pairs of rims on one side, nozzle on the other, is common in planetary nebulae and in cluster cooling flow, where we know the shaping is by jets. This tells me that the explosion of core collapse supernova, this supernova was by jet. Here are 2 images of the same supernova remnant, and you see many pairs, actually 4 pairs, identified pairs of clumps. So these four pairs of clumps are common In planetary nebulae, here I give you 4 planetary nebulae with pairs of clumps, and there are many, many more. There are more pre-planetary nebulae, post-AGB star with clumps. This is very common. This is shaping by jets. Again, Vela supernova was exploded by jets, and this is my summary for you to read. I'll stop here.
May I ask you, so you connect the fact that you see jets with the idea that jets are causing the explosion. Couldn't it also be the case that these jets are the consequence of the neutrino-driven explosion?
Why should it be? I don't know. Nobody worked it out. But your question is good, because in the jittering jet explosion mechanism, I didn't talk about the jittering jet explosion mechanism, but because I don't have time here, but the model is based on jets that going in different direction because of stochastic angular momentum accretion. Now, after you launch the jet and it starts to explode the star in the inner core, neutrino heating add to the energy. This is first. Second, the people who support the neutrino-driven explosion mechanism claim that all this shaping comes with jets, if there are jets. And we know of several cases that there are jets in Cassiopeia, which you see here on the right, with the many, many lines. This is Cassiopeia. They claim that, and we know there is a jet here, and it's silicon, and it's silicon and magnesium rich, so it must come from the explosion. They claim that these are post-explosion jet and not related to the explosion mechanism. This is hard to explain because the energy in the jets is very large. It's like the explosion energy, because you see shaping that, like, look at 87A on the lower left. The structure shaped by jet is the main ejector. So it must be very energetic. The jet must be very energetic. So it must be fine-tuning that we have explosion with neutrino, and then the jets come and have the same energy of the explosion. I find it unlikely, but I cannot give you a proof that there's no explosion with neutrino and then come the jet to explode. But I can tell you that the neutrino simulation have many problems. Some of them admit the problem, some of them do not admit the problem. For example, the different groups do not agree on the results. They don't get high energy. They never get energy more than about 1 time 10 to the 51 erg, and we see some supernovae more energetic.
Hi there, thank you for your talk. So my question is about the jets shaping planetary nebulae. So since AGB stars do not explode, where does the energy from the jets come from?
The jets come from accretion to a companion. We don't know how to launch jet in a single AGB star, and some planetary nebulae are circular, and we think these are single AGB star, maybe have planets. I think some of the very mildly elliptical circular have planets companion shaping. This is model going 30 years ago. But in all planetary nebulae, all of them, we have companion that accrete mass and launches the jets. And the energy comes from the accretion energy onto a main sequence companion, maybe a white dwarf companion. In core collapse supernovae, the energy comes from accretion into the newly born neutron star. So it's gravitational energy. The energy is gravitational, not nuclear.
Thank you very much for a nice talk. My question is, why there's a puzzle mentioned in your first part of your talk that there should be an outburst before their explosion of the type 2b supernova, or to say which kind of outburst it should have at the progenitors of type 2b supernova?
Yeah, you talk about the first part, because we don't know yet what caused the outburst, but there are several models. One of them is that just before explosion, years, 2 weeks before explosion, because of very, very strong nuclear burning in the core, most of the energy goes to neutrino that take the energy away and escape. But some energy forms very strong convection in the core, which excite waves that go to the envelope and cause envelope expansion. And if you have a binary, then interaction with the binary can, binary accretes mass, and you have energy that eject compact circumstellar medium. And indeed, in some cases, we see outbursts 1 month or maybe few years before the explosion, which eject a circumstellar medium. And it comes probably from the core activity. But in those 2 supernovae, one a year ago, one 3 months ago, we do not see outbursts for many years before the explosion. So the compact circumstellar medium, which we know about it, because the ejecta of the supernova collide with it, and we see narrow lines because this circumstellar material moves only at 100 kilometers per second, not at 1,000 kilometers per second. Second, we see extra light because of the collision, cannot come from an outburst. So I think it's a long-lived extended envelope, and I think we also have it in AGB stars. And I think some binary interaction in AGB stars with high luminosity towards their end, and also those that have strong convection and pulsation, also have effervescent model, namely bound clumps that go up and down. So the puzzle is for a model that say that any compact circumstellar material in pre-core collapse supernovae come from outbursts. This model cannot explain these last two supernovae.